All right, good morning, everybody. This is College Algebra, April the 16th, and we are rapidly finishing the semester. And after today, believe it or not, after today, two more lectures, and that's it for the semester. So we are just about finished. A couple of announcements. First of all, your next WebAssign homework is due April the 24th. So if you just have a little bit more than a week to do that, that will be a week from tomorrow, I guess. So April the 24th, and that's almost finishing up your WebAssign homework. Not quite, but pretty close. Just a couple of things about this week. I just wanted to kind of run it down here day by day. So today we have lecture at 9 o'clock. Tomorrow I have online office hours 11 to noon and 8:30 to 9:30 in the evening. Wednesday, no lecture, as Jennifer and I were just talking about. And I will be on campus on Wednesday for on-campus hours 4 to 6 p.m. Remember that when I say on campus, my office is in the Winship building on the North Harris campus in room 115K. So please, I try to encourage people to come by and see me during my on-campus hours before each exam. So I'll be on campus on Wednesday 4 to 6. On Thursday, I'll be on campus again, 9:30 to 11:30 in the morning. And then on Thursday, the exam 3 window opens and runs from the 19th through the 24th. On Friday and Saturday and Sunday of this week, I can be available online by appointment. So on Friday, Saturday, and Sunday, if you do want to come by outside of my regular hours, email me or send me a remind message, and we'll see if we can work out a mutually agreeable time where I can meet you in the WebEx office for some help. I'd be happy to do that. And then on Sunday, again, I'll be online from 8:30 to 9:30 in the evening. All right, so today we're going to finish up solving log equations, and that will be on your exam that starts this week. So I'll put a dashed line here, and this is exam 3. Above the line right here, and then below the line on final exam only. Right? By the way, mentioning the final exam here, I guess I should have mentioned this, but I will be posting a review for the final exam. I have a pretty good review put together over the years that I kind of redid a little bit in the fall, and so I will be posting that. If I get time, I will post the final exam review sometime this week. If I don't get time, it'll be early next week. But I'll try to get to that this week and post that. It's the same place all of your exam reviews go. And so be looking for the final exam review, relatively soon. All right, so we are talking about equations as we're coming out of all the stuff we've done with exponential and logarithm functions. We were talking about equations. And so the first thing I want to do is I want to kind of give you a good overview of everything we've done with equations so you know how it all fits together. This is all on your exam this week, and so this will be a good review on equations. And this is going to be a significant topic on your exam. So remember, we talked about exponential equations. And then with exponential equations, we split those into two categories. Ones where we use rules of exponents and ones where we use logarithms. So let's see, rules of exponents there, and then properties of logs here. So recall that with a problem where you're using rules of exponents, so for example, if we have 25 to the x plus 3 equals 125 to the 2x, as an example. So that's an equation where you use rules of exponents or properties of exponents to solve the equation, because recall that you can get the equation to look like this in a problem like this, where you get b to the x equals b to the y, where the bases are the same, right? 25 and 125 are both powers, in this problem, are both powers of 5, right? 25 is 5 squared and 125 is 5 cubed. And because those are both powers of 5, you can use properties of exponents to solve this type of equation. This is 5 squared to the x plus 3 equals 5 cubed to the 2x. Right, and then multiply exponents in both cases on both sides of the equation, right? Because that's the rule of exponents that you use there, is you multiply exponents there. And so you get 5 to the 2x plus 6. Don't forget to use the distributive property when you multiply there. Equals 5 to the 6x. And then remember what happens here is once you get the bases to be the same, you're using the idea that x has got to be equal to y, right? That's the property. That when you get b to the x equals b to the y, then the exponents have to be equal. And you don't have to remember the rule as far as the way it's stated like that, but remembering it in words wouldn't be bad, right? When the bases are the same, then the exponents have to be the same, right? And so you get 2x plus 6 equals 6x, and then solve that equation. You get 6 equals 4x, or 6/4 equals x, which is 3/2, right? And that's your solution to the equation right there. So this is a problem, no logarithms involved, right? All you're doing is using properties of exponents. And then we had exponential equations where you did have to use properties of logarithms. So if you have, for example, if you had 5 to the 3x minus 1 equals 15. Okay, 5 to the 3x minus 1 equals 15. 5 and 15 are not powers of the same number, right? There's no way, 15 is not a power of 5. And so you can't use properties of exponents here. You have to use properties of logarithms. So you take the log of both sides of the equation. And don't forget that here what you're doing is you're using this property. You're using the fact that if two numbers are equal, then their logarithms have to be equal also. And I wrote the property so it's base 10 logarithm, but remember it can be any base logarithm you want. It doesn't matter. Because you're using your calculator here, you're going to either use base 10 like I did on this problem, or you're going to use base e, one or the other, which is the natural logarithm. Right, so I took the log of both sides of the equation here, used the power rule for logarithms, and you bring that exponent down in front, the 3x minus 1. Don't forget to put the 3x minus 1 in parentheses. Equals log of 15. And then we saw how to do this kind of, solve this kind of equation in lecture before. You divide by log of 5. This is probably the quickest way to do this. So you divide both sides by log of 5. So that just gives you 3x minus 1. And then you add 1. You have log of 15 divided by log of 5 plus 1. And then finally divide by 3. And it looks kind of nasty. It looks like an ugly expression here because you're dividing that entire fraction expression by 3. Remember, it's the whole thing divided by 3. But that's not a hard problem to enter on your graphing calculator at all. And so you'd enter that on your graphing calculator, which you should practice before you get to the test. Don't discount the fact that sometimes students get confused as to how to enter these things on a calculator correctly. So please watch for that and practice it before you actually take the exam. So like in this problem, what I would do is I would practice making sure I can enter this. I just did this, and I got approximately 0.894. I'll probably ask you to round to either 3 or 4 decimal places. So this is about 0.894 right here. Don't forget when you enter this in your calculator that you've got to put the entire numerator in parentheses, like that. Notice I put the entire numerator in parentheses. All right, so that's a problem. So it worked. This is one thing we've done in class then is we've looked at exponential equations. We've looked at exponential equations where you have to use rules of exponents because you can get the bases to be the same. And we've looked at exponential equations equations where you have to use properties of logarithms to solve the equation, because both sides of the equation are not powers of the same number. Also, I'm looking at logarithms, exponential equations with logarithms there. So let's look at one more equation like that. Let's say we have 2 times e to the x plus 3 minus 10 equals 40. That's also a problem, when you have a base of e. That's also a kind of problem where you have to use properties of logarithms, right? So remember, you have to get the exponential expression by itself first, so isolate that before you use logarithms. So I add 10 to both sides and then divide by 2. And you see now how I've got the exponential expression by itself. And then because the base is e, this is a problem where you use ln for sure. You do not use log base 10 here. The problem's much easier if you use ln. Right, you bring the x plus 3, the power, down in front, and that leaves you with ln of e equals ln of 25. And ln of e, remember, is equal to 1. That's why we use natural log here, because the natural log of e, which remember represents the power you raise e to get e, is going to be equal to 1. So this just gives you x plus 3 equals the natural log of 25. And then subtract 3. I'll put that at the beginning here. You could put it at the end also. And this is another problem where you'd use a decimal approximation. So let's see, negative 3 plus natural log of 25. And I get approximately 0.219 to 3 decimal places for the solution to that equation. And obviously I'm working, there's a reason why I work these problems specifically as examples. These are all similar problems to things you would see on the exam later in the week. But I wanted to kind of get, and I'm also trying to give you just kind of a bigger overall picture of what we've been doing with equations, with exponential expressions and logarithms. Okay, so these are the kinds of problems where we were looking at exponential equations, some with rules of exponents, some with properties of logarithms. And then we moved on to log equations, and we have looked at one type of logarithm equation so far, and we did that last time, where you get a logarithm equals a constant, right? And so I actually kind of divided these into 2 groups, and we've done the first group already. So sometimes I call these type 1 log equations, where you get the logarithm of something equals a constant, right? And so I'm going to look at another example or 2 of those. And then type 2 log equations are ones that you have to write it logarithm of something equals logarithm of something else, right? And it doesn't matter what the base is, by the way. It doesn't matter what the base is in any of those. So you either get logarithm equals a constant, that's what I call a type 1 log equation, or you get logarithm equals a logarithm, which is what I call a type 2 log equation. Excuse me. All right, so in a problem, for example, so let's look at some type 1s again. So if we have just this kind of problem here, 2 natural log of x plus 3 equals 7. See, that's a problem where you see how there's some terms in there that are constants that are not logarithms. And so that's an example, that would kind of be a tip-off there that this is a type 1 log equation. So you get the logarithm by itself. Isolate the logarithm, just like with exponential equations. So you subtract 3 and then divide by 2. Whoops. And see how you get the logarithm by itself. All right, so now what you do is you write in exponential form. Remember, that's how you solve this type of equation. You write in exponential form. Now remember that the base on this logarithm is e, right? Because this is logarithm base e. Remember, that's what the natural log is a shorthand notation for. And so in exponential form, this would be be good if I wrote it right. Be e squared equals x. Remember that a logarithm is always equal to the exponent, so that 2 has to be the exponent. So you get x is equal to e squared, and you've solved the equation. On a calculator, go ahead and find what e squared is. And I get 7.389 approximately. All right, and so that's e squared. And don't forget, on a calculator, that would be entered as second. You have to hit the second key first there, and then ln, and then 2. Okay. Okay, so that's an example of a type 1 log equation. Another example, let's say we have logarithm base 3 of x plus 2 plus logarithm base 3 of x minus 2 equals 2. Like that. All right. So first thing you have to do is, if you want to get this as a logarithm equals a constant, you have to combine these logarithms. And you combine these using the product rule, because it's an addition problem. So this is log base 3 of x plus 2 times x minus 2, like that. And so that would be log base 3 of x squared minus 4 when you multiply that out. See, and now it's logarithm equals a constant. And so now you write it in exponential form. So I write it in exponential form. And this would be, remember, the logarithm is equal to a constant. I'm sorry, is equal to the exponent. It is a constant, but it would be equal to the exponent. So you'd have 3 squared equals x squared minus 4. And if you would prefer to write it as x squared minus 4 equals 3 squared, obviously that's the same thing. So that would be x squared minus 4 equals 9. And so that gives you x squared equals 13. And then be really careful here. This is x equals plus or minus, because you're taking the square root of both sides of the equation, because that's how you're solving this. It's a quadratic that you can use the square root method on. So when you take the square root of both sides, you have to use a plus or minus. And you get plus or minus the square root of 13. Now this is something I did not get a chance to talk about last time at all. So this is new as far as lecture here. Is negative square root of 13 cannot be a solution to this equation. And the problem with the negative square root of 13 is that if you tried to check it, so if I checked x equals negative square root of 13, when I put that in the logarithm, like with the very first one, like that for x, the problem is negative square root of 13 is like negative 3 point something or other. When you add 2, you get a negative number. And you have the log of a negative number here. And that is not allowed. Remember that when you find the domain of a logarithm, that number has to be positive. And sometimes when you solve log equations, you end up with a negative number, the log of a negative number, and you have to throw that out. So negative square root of 13 is an example of that here. So throw negative square root of 13 out of the solution set. So the moral to the story with log equations is that you have to make sure that you don't get the log of a negative number when you try to check a solution. And that is an issue with logarithm equations. Is you can do everything right And there's not a problem with anything you're doing at all, but sometimes you get these extra solutions at the end that can't really be solutions to the equation, to the original equation, and so you have to throw them out. All right, so I wanted to kind of call that to your attention that could definitely be an issue, is that you're going to get logs of negative numbers sometimes. So you have to be really careful about that. All right, let's look at another. So we're going back over type 1 logarithm equations right now, right? So we're looking at equations where you can get the equation in the form of logarithm equals a constant. Notice that's what I'm doing here, is I'm looking at a logarithm equals a constant. Put red boxes around those places in each of these problems. So the next one, let's say we have log base 4 of 5 minus log base 4 of x plus 3 equals, and we'll say 3. All right, so since there's a constant term, that 3 over there, we can get this equation as a logarithm equals a constant. I combine these two logarithms using the quotient rule, right? Because it's subtraction. And so this gives me log base 4 of 5 over x plus 3. And so you get log base 4 of 5 over x plus 3 equals 3. And then you solve this equation, and this may turn out to be kind of ugly, but you write it in exponential form. Remember, that's the idea here, and you get 4 to the third power equals 5 over x plus 3. Remember, the logarithm is equal to the exponent, so that 3 has to be the exponent. The base on the logarithm and the base on the exponential expression are the same, so that's why it's 4 to the third power. So you get 64 equals 5 over x plus 3. This doesn't turn out especially nice here at the end. You multiply through by x plus 3 to clear the fractions. So that gives you 64 times x plus 3 equals 5. And then you multiply this out. You get 64x plus 192, oh my gosh, equals 5. And then subtract 192, you get 64x is equal to negative 187. Yuck. And then that gives you x equals negative 187 over 64, which is not too far away from negative 3. It's not negative 3, but it's relatively close to negative 3. And actually, so does this give you the log of a negative number? This is actually something to kind of pay attention to here. 187 divided by 64, just as a decimal, is about 2.92. So you get about negative 2.92 right there for x. And so do you get the log of a negative number? Don't throw the solution out just because it's negative. Do you get the log of a negative number? So do you get the log of a negative number with this solution? And the answer here is actually no, you don't. If you try to check it, right, you get log base 4 of 5 minus log base 4 of, and what do you get here? Negative 187 over 64 plus 3 equals 3. And then the question is that crazy number inside the parentheses, is that positive or negative? Well, don't forget that number, negative 187 over 64, is approximately negative 2.92. Plus 3, that's a positive number. That's all you really care about, is it positive or negative. And so you get the log of a positive number here. And so this is going to be a solution. And so we would just write negative 187 over 64. So don't think just because you have a logarithm equation that you can't get a negative number as a solution. What you're worried about is, do you get the log of a negative number? That's what you don't want. Okay, that's what you have to be careful about. All right, so that's a look at logarithms that are. Well, I tell you what, I'm going to look at one more problem. Okay, I'm done with that. So now we're going to go on to type 2 logarithm equations. So these are equations that you can write in this form. Logarithm of A is equal to logarithm of B. It doesn't matter what the base on the logarithms are. And when you can get an equation to look like that, then what has to be true is that A and B have to be equal to each other. Okay, so this is an example right here. Let's say we have log of 3x minus 2 minus log of 2 is equal to log of x plus 4. So you see how every one of those terms is a logarithm. So this is a type 2 log equation. And so what you do, first of all, combine these logarithms so that you get 1, and that would be a quotient rule, right, because it's subtraction. So you get log of 3x minus 2 over 2 equals log of x plus 4. And now you've got log A equals log B. Right, log of one expression equals the log of some other expression like that. And so what has to be true? The A and the B values have to be equal. That's the only way this could be a true statement. So 3x minus 2 over 2 has got to be equal to x plus 4. So it's kind of like you're dropping the logs. It's not really what's happening. You're really saying that the first statement implies the second statement. Right? If a logarithm of two numbers are equal, then the two numbers have to be equal, is what you're saying. And now solve this equation. So you multiply through by 2 to clear the fractions. So you have 3x minus 2 is equal to 2 times x plus 4. And then solve this equation. So you have 3x minus 2 equals 2x plus 8. Subtract 2x and you get x, and add 2 and you get 10. So you get x equals 10. And again, you could check that. You don't want logs of negative numbers there. And if you want to walk through the whole check, you certainly could do that. If you go to the original equation, you have log of 3 times 10 minus 2 minus log of 2 is supposed to equal log of 10 plus 4. And if you see what I did there, every place I saw an x, I substituted a 10. Right? If you go to the original equation, every place where there's an x, I substituted 10 in its place, because that's what we found the solution to be. So I get log of 3 times 10 is 30, minus 2 is 28, minus log of 2 is equal to the log of 14, we think. Right, and then what about log of 28 minus log of 2? Well, that's a quotient rule problem, so that would be log of 28 over 2 equals log of 14, and you can see that that's going to check. You get log of 14 equals log of 14. So 10 is our solution here. All right, that's the solution to this equation. Okay, so we've solved a logarithm equation, a type 2 logarithm equation, where we could get a logarithm equals a logarithm. The next problem, if we have the natural log, so we're looking at some examples now of these type 2 logarithm equations. You have the natural log of x squared equals the natural log of 2x plus 3. That's a logarithm equals a logarithm, so it's already in the right form. And so what has to be true here? The x squared and the 2x plus 3 have to be equal to each other. Right? This is a logarithm equation just like the last one. And so now this is quadratic. right? And so remember what you got to do here is set that equal to 0. So if I subtract 2x and subtract 3, I get 0. And then I solve that quadratic, so I can factor that. This factor is x minus 3 times x plus 1. Set each factor equal to 0, and I end up with 3 and negative 1 as solutions. And this is another place where you would check to make sure that you don't get the log of a negative number anywhere in the equation. You could check negative 1 in particular, because you might be worried about negative 1 in particular because it is a negative number. But notice that, no, it doesn't cause us a problem, because when you substitute negative 1 in place of x, you get logs of positive numbers. Right, because the natural log of negative 1 squared is 1, so you get the natural log of 1 on this side. And remember, the log of 1 is 0, by the way, so you get 0 on the left side. And on the right side, you get negative 2 plus 3 inside the parentheses, and so that's also natural log of 1. And so you do get 0 equals 0 there. Right, so negative 1 checks, just like 3 checks also. So 3 and negative 1 are solutions to this equation. All right, so that's a good example there of a type 2 logarithm equation. So let's look at another example of a type 2 logarithm equation. So let's say we've got this problem here. Let's see. So we've got log base 8 of x plus 6 minus log base 8 of x equals log base 8 of 58. And so notice all of these terms in this equation are log base 8 terms. There's no constant terms anywhere. These are all log base 8 terms. And so this would be a type 2 logarithm equation. Right? And we can get it as logarithm equals a logarithm. Once again, we combine those two terms using the quotient rule. And so you get log base 8 of x plus 6 over x equals log base 8 of 58. Right, I had to combine the two logarithms on the left side using the quotient rule because it was subtraction. And now what has to happen? Well, these two numbers have to be equal. Let's see, if x plus 6 over x equals 58. Clear the fractions by multiplying both sides by x. And you end up with x plus 6 equals 58x. And let's see, if I subtract x, and I get 57x. And then divide by 57. And I get x is 6 over 57. Believe it or not, there's a common factor there of 3. So you get 2 over 19. You can check to make sure, but that's certainly not going to give you the log of a negative number there. And so 2/19 is going to be the solution set for this equation. Okay, so hopefully, let's see, I will work one more problem that's a type 2 log equation. And then that will be it for this kind of problem. So, so let's say we have the log of x squared plus 13 equals log of 7x plus 3. All right, let's see how this works out. So this problem is definitely already a type 2 in the form it's in. It's a logarithm equals a logarithm. So, so this is already log of a equals log of b. And so I know that a has to be b. So that x squared plus 13, which is my a there, has to be equal to 7x plus 3. Right, that has to be true. If the first statement's true, then the second statement has to be true. This is also a quadratic equation. We would set it equal to 0. right, to solve that equation. So let's see, I'd subtract 7x, subtract 3, then I get x squared minus 7x plus 10 equals 0. Factor that, you get x minus 2 times x minus 5 equals 0. And then you set each factor equal to 0, and you end up with 2 and 5 as solutions. And so, and both of those would be fine. If you try to check those, you'll find that neither one of them gives you the log of a negative number. And so those are both going to be solutions to that log equation. All right, so, so 2 and 5 are definitely going to be solutions there. All right, so let's see. Let's look at this problem right here. And then let's see if you can tell me what kind of a log equation this would be, whether it be type 2 or type 1. So let's say we have the natural log of 3 plus the natural log of 4.4x plus 6.8 equals 2. So is this an equation that is a type 1 or is it type 2? In other words, because this is something you're going to have to address on the test. So remember, type 1, so is this type 1? And type 1, remember, is where you have a logarithm equals a constant. Or is this type 2, where you have a logarithm equals a logarithm? Right, and we'll put a capital A and a capital B in there. Right, and what happens, I mean, how do you know which one of these it is? Well, it's this 2 is the tip-off right here, right? That's a constant. It's not a logarithm at all. And so that indicates this is going to be a type 1 logarithm equation. All right, and so that's how you're going to solve this equation. Sometimes you're going to have to answer that question before you get started in the problem. So you combine these two using the product rule. Product because it's an addition problem. So you have the natural log of 3 times 4.4x plus 6.8. The fact that there's these nasty decimals in there shouldn't matter to us at all because we have a calculator. Right? So that shouldn't be a problem. So go ahead and multiply through by 3. And let's see, what do you get there? 13.2x plus, let's see, 3 times 6 is 18, and then 2.4, so I get 20.4 right there equals 2. And now what you do, remember, is write in exponential form. And the base on this logarithm is e, so you're going to get 13.2x plus 20.4 equals e squared, like that, right? The base is e on the logarithm, so it's that base raised to the exponent 2 is equal to 13.2x plus 20.4. I would just leave it, to be honest with you, as e squared until you're ready to solve at the end. So I would just leave it that way. And then solve this for x. So I subtract, let's see, let me write this up. So I'm going to subtract 20.4 and then divide by 13.2. So you have e squared minus 20.4 divided by 13.2. And then that's a place where you would bring in your calculator to do the calculations there. So I get e squared minus 20.4. I'm going to do that calculation as an intermediate calculation here. So that gives me negative 13.0109, like that, divided by 13.2. And then I'm going to divide that by 13.2. And I get just a little bit, pretty close to negative 1. You get x equals negative 0.986 approximately to 3 decimal places. And so that would be the solution to this equation. You do need to make sure you don't get logs of negative numbers, but you're not going to on this. So that's going to be the solution set to this equation, right? Approximately negative 0.986, like this. All right, so that finishes our discussion on exponential and logarithm equations. Kind of a good overview of all the different kinds of equations we've talked about. And so now what we're going to do is we're going to leave exponential and logarithm equations behind altogether here. If you go on in mathematics at all, you're going to look at applications. So especially if you're a science major, if you go on and take trig, pre-cal, calculus sequence, you'll look extensively, like in pre-cal especially, and then again in calculus, you look at a lot of applications that involve exponential and logarithm functions. Very, very many of those kinds of applications exist. We just unfortunately don't have the time to cover those. So I've done a little bit with compound interest, but that's the best I'm going to do with applications in college algebra. So what we're going to do now is we're going to turn our attention to the last topic, essentially, of the semester for us, and that is systems of equations. And we're going to finish the semester talking about systems of equations. We cover this mainly, not completely, but mainly for business majors. Now, science majors will need to deal with systems also, but we're putting this gets put in the end of college algebra mainly for business majors because you have to go on and take finite math, which involves systems of equations and in certain types of applications, and some things with matrices, and so that's what you have to look at. So what we're going to do is I'm just going to give you, because I'm going to give you some reminders here on what systems of equations are, and then we'll pick up with this again next Wednesday with our next lecture. But you need to get some kind of a footing underneath you as far as systems go if you're going to be able to deal with that. So first of all, you should have already taught someplace in your algebra careers of systems of two linear equations and two unknowns. Sometimes called a 2-by-2 system. So this is an example of a 2-by-2 system. 2x plus y equals 8, and 3x minus y equals 2. Right? That's what we call a system of equations. And what you're looking for is you're looking for an ordered pair, looking for ordered pairs that make both equations true. Right, and with 2x plus y equals 8 and 3x minus y equals 2, you can solve this. And remember, one method for solving this type of system is called the elimination method. And the elimination method involves adding the two equations together. And you've got things lined up in columns, so you add the equations. And when you add the equations, what happens here? The 2x plus 3x gives you 5x. But notice what happens to the y's. Well, the y's get eliminated, right? A positive y minus y is 0. That's why it's called the elimination method. Equals 10. And so this gives us x equals 2 right away, right? You get 5x equals 10, which is an equation in one variable. That's a goal. You want an equation in one variable, and then you solve that equation, right? So you solve it, and now what you do is now find y. And you find y by taking one of the original equations, for example, 2x plus y equals 8, and you substitute 2 in for x. So this is a pretty straightforward, pretty simple method. You get 4 plus y equals 8. Subtract 4, and you get y equals 4. And so the ordered pair solution, 2, 4, and you can check this certainly, but 2, 4 is the one ordered pair that makes both equations true. Right, there's lots of ordered pairs that make one of the equations true. 2, 4 is the only ordered pair that makes both equations true. So, the elimination method, it works out fairly nicely. The problem is, what I gave you a system right there where the y's were eliminated by just adding the two equations together. So what happens when it's not quite that straightforward? So if you have 3x plus 5y equals 10 and 2x minus 3y equals 8, this one will probably turn out to be kind of ugly. Notice if I just add the equations together like this, neither variable gets eliminated. So neither x or y is eliminated when added. Is eliminated when adding equations. So what do you do here? Well, now you force one of them to drop out. And you do that by picking a variable that you're going to eliminate first. So let's eliminate y. And so to eliminate y, what you do is you multiply each equation by a constant so that the y's will drop out when you do add the equations together. So if I multiply the first equation by 5 and the second equation by 3, well, that won't work. I don't know why I'm doing that. That's kind of crazy, right? So if I multiply the first equation by 3 and the second one by 5, that's so much better. So then what happens here, you get 9x plus 15y equals 30, and 10x minus 15y equals 40. And now y drops out. Right now y is eliminated. And so you add the equations together, and you get 19x equals 70. I told you it's going to be ugly. And then you divide by 19, and you get 70 over 19. Now, what you could do is you could substitute 70 over 19 into one of the original equations. You could certainly do that. But what's probably easier to do here is to take the original system and now just go through and eliminate x instead of y. So eliminate x. So now eliminate x. And so I'll do that by multiplying the first equation by -2 and the second one by 3. And when you do that, you get -6x minus 10y equals -20, and positive 6x minus 9y equals 24. And when you add these equations together, the x's drop out, and you get -19y equals positive 4. And then divide by -19, right? And you get y equals -4 over 19. So an ugly solution, but it's still not bad. The arithmetic is a little messy, but you get that 70 19ths, -4 19ths would be the solution to this system. That would be the one ordered pair that makes both equations true. Now, graphically, what you're doing here, when you solve these, graphically, what you're doing when you solve these kinds of equations, these kinds of systems, here is you're looking at the intersection of two lines, right? With your linear systems right here, right? What we just found on these first two problems is if you if you were to graph both of those equations, right, each one of them would have a graph that's a line, and so the solution to the system is the point of intersection of the two lines. Right, so the solution to the system is the point of intersection of the two lines. And that makes sense, right? All the points on one line make one equation true. All the points on the other line make the second equation true. So the one point that makes both equations true would be the one point that's on both lines. Now, the problem is that they don't have to cross, do they? So you could easily have a system where the two lines are parallel, like this one is right here. Right, and in a system like this, where the two lines are parallel to each other, right, so a system, let's see, so a system where the graphs are parallel lines have no solution, or has no solution, I should say it that way. Right, there's no ordered pair that makes both equations true. This type of system is called an inconsistent system. Right, if it's inconsistent, no solution to the system. And then another possibility is that the two lines intersect, but they're actually the same line. So they intersect everywhere on the line. Right, so two lines that are the same line like that have an infinite number of systems. They have an infinite number of solutions. So a system where the graphs are the same line has an infinite number of solutions. And this type of system is called a dependent system. It's dependent if the two lines are the same line, like that. All right, so now those are things that should just be reminders of things that you have done in your past algebra lives. What we want to bridge into from that is that you can also have systems. In fact, in many ways, more important systems to solve are called nonlinear systems. We've been talking about linear systems where the graphs are all lines, but a nonlinear system is a system where one of the graphs, at least one of the graphs, is not a line. So as an example, if we have this system right here, y equals x squared, and you should know, based on what we've done this semester, you should know what that graph is, and we'll talk about that in a second. And let's say we have x plus y is equal to 2, x plus y is equal to 2, then that particular system is called a nonlinear system because the first graph is not a line. In fact, remember that y equals x squared is a parabola. So you're still looking for where the two graphs intersect each other. So y equals x squared we know is a parabola, right? It has a vertex at 0, 0, goes through 1, 1 and negative 1, 1, 4, 2, 2, 4 and negative 2, 4, like that. And so here's the parabola like this. And then we got x plus y equals 2, and x plus y equals 2 is a line right, that has intercepts at 2, 0, and at 0, 2. So it goes through 2, 0, and 0, 2, and that graph is a line that looks like this. Right, so what we would be looking for is the point of intersection of those two graphs. And it looks like from the graph, we got the two solutions. So from the graph, it looks like 1, 1 and 2, 4 are solutions to the system. And so what we're going to do is we're going to explore how to find that solution to that system and algebraically. So we're going to look at that algebraically, but I think we're going to do that next time. So next time what we're going to do, and let me give you kind of a overview of the rest of the semester. So next time, when I say next time, our next lecture is going to be April 25th, right? We skip Wednesday of this week and Monday of next week because of exam 3. And so on April the 25th, on Wednesday, so not this Wednesday, but the following Wednesday, we're going to look at nonlinear systems algebraically. And so we've started talking about nonlinear systems here, so that's good. So nonlinear systems algebraically, and we're going to look at elimination as a method and substitution, which we have not talked about, but you should have talked about somewhere before in your lives. We're going to talk about substitution as a method for solving nonlinear systems. And then we're going to start talking about, we're going to go back to linear systems, and we're going to start talking about 3 by 3 linear systems. And we're going to use matrices to do that, so using matrices. And then the last lecture is going to be on the 30th, so that's April the 30th. And we're going to look exclusively at 3 by 3 linear systems using matrices. And so we'll start that on next Wednesday, and we'll finish it the following day, following lecture. And that will pretty much finish up our semester. And let me say using matrices again here. All right, so this gives us a really good start on systems of equations. So that's a big plus for us as we go in, because 3 by 3 linear systems using matrices takes a while to get through. So that will give us a good length of time to spend on that, which is good. So, all right, does anybody have any questions?
I'm good. I'm good.